Cars have become absolutely essential to modern life. We couldn't enjoy the advantages we have become accustomed to without them. Now there is a growing global demand to keep enjoying the advantages our cars offer us, but without the trouble of having to drive ourselves. We want to put technology in the driving seat and be chauffeured around. Technology, though, is struggling to reproduce anything like the brain's awareness and flexibility needed to drive us around safely. What our brains do almost effortlessly is causing a huge headache for the automobile industry. Given the brain's superiority, technology would do well to learn how it achieves this. And this is exactly the approach of Dreams4Cars. The Dreams4Cars project began by looking at what is supposedly going on in the brain while driving. Visual information is transmitted from the eyes to the visual cortex at the back of the brain, where the signals are processed and identified. As the visual input is further processed forward along the dorsal stream, motor-related brain cells are activated, which generate possible responses to the sensory data. Of all these possible actions, the one most urgent and effective is selected by the basal ganglia loop, based mostly on previous similar situations. However, before the command is transmitted to the motor system, the basal ganglia enables us to take decisions based on the priorities of the particular occasion. This requires input from the frontal cortex, which enables us to bias towards actions that are more difficult in the short term, but have a longer term reward. For example, on one occasion, we may not overtake when it is safe enough to do so, because we left early and have plenty of time to enjoy the journey. Other days, we may be short on time, and instead of remaining in the safer position, prefer the more difficult short-term overtaking maneuver to gain the longer-term reward of getting to where we're going quicker. When these preferences or biases are evaluated, the command is transmitted to the motor system. The command is also fed to the cerebellum, which feeds back into the sensory areas and the dorsal stream. As data re-arrives there, representations or internal images of what is about to happen on the road are anticipated ahead of time. Possible reactions to these anticipated images are generated, as well as their consequences. In other words, this loop produces our quick, often life-saving reactions. The more this loop experiences driving situations, the better we learn to operate the controls of the car and react. Let's now have a look and see how the Dreams4Cars Brain, or agent as it is called, is based on the human brain processes we have just been looking at. The agent receives sensory data, but of a different kind, through electronic sensors, cameras and radar. This sensory data is transformed by a neural network with many layers that functionally works like the dorsal stream. The network combines data into patterns that take the form of humps of activity across the neural layers, encoding the control required for different actions. All these potential actions are fed into a decision-making algorithm, which carries out robust action selection in a way similar to the basal ganglia. A biasing or preferencing mechanism is created within the algorithm to represent specific driving strategies on any given day, for example, whether haste is needed or steady cruising. This imitates the role of the frontal cortical loop. Meanwhile, the agent's equivalent of the cerebellum is a trainable neural network. It collects motor commands and sensory data which will be used to create internal driving models, thereby allowing predictions of what to do next. This learning takes place in a simulated or offline environment, allowing the agent to know how much gas, brake and steering to apply to achieve the desired response. In this way, offline learning in the simulator can enhance the effectiveness of the closed control loop. In our brains, all of the activity we have been talking about occurs in a split second. It then reoccurs continuously during the maneuver. That's a lot of thinking. It's a huge amount of perception, selection and motor control to be done and redone by an artificially intelligent system attempting to mimic the brain. Before we give up hope of today's technology being able to operate so quickly, it is worth remembering that a huge amount of learning and simulation had to be done in our brains before any of us actually drove a car for the first time. We spent years learning to coordinate our actions, observing and familiarizing ourselves with the world. This experience, in essence, is simulation, preparation to do it ourselves. Similarly, the Dreams4Cars brain has to be taught through much repetition until it can feel its way around in the world. So the Dreams4Cars agent begins its driving life not on the road in a car, but by familiarizing itself with its environment and its own abilities. And it does this in a very human way, by dreaming about driving. To enable this, the agent has created a virtual world for itself to operate in, generated by episodic and embodied simulations. It functions just as it does in the real world, with the same mathematical algorithms, neural networks and feedback loops. It receives sensory data in exactly the same way as it does on a real road. It then uses reward-based learning to try out all kinds of scenarios, resulting in it being able to not only evaluate how it performed, but with each dream or simulation, learn how to improve its response in each situation and how to operate the car to achieve the appropriate maneuver. Being in a virtual world means the agent can run scenarios that would be too dangerous to try out in the real world as many times as it likes, until it is able to learn what is safe and effective. Not only that, it takes the data it collected while driving or awake and simulates alternative responses, and is actually able to work out what would have happened in each of those alternative scenarios. Human dreams often go beyond the realms of reality to extraordinary and unique situations that couldn't have been otherwise imagined. For example, in a dream, a memory of a butterfly and an elephant are easily recombined into a visual experience of an elephant flying off with butterfly wings. When the Dreams4Cars agent creates scenarios, it is not only recreating real data, but through episodic simulation, also imagines extraordinary and unusual scenarios, and in this way covers a huge range of road eventualities not thought of by engineers. For example, in the virtual world, the agent may imagine forgetting to apply the handbrake at the edge of a precipice, or may imagine another driver forgetting to give way, having only seen some cars given way late. It can keep dreaming until it has perfected its responses to more and more road-like situations, both common situations and unusual ones. How perfect these responses are need to be then tested in a real car in the real world. So the agent is in effect woken up and put in a test car on a test track, where its dream learning is evaluated in the real world, not only by engineers, but by itself. Any discrepancy between the dream and real world creates focal points for new simulation scenarios the next time the agent dreams again in the virtual world. And so the agent goes back and forth between dream to wake state, narrowing the gap between dream and reality, until, like us, it has had enough experience to be able to drive our vehicles safely for us.